messages. So yeah, I'm recording this now. So if we take a look here, see if I can stop share. How do I stop share? There it is. But if we take a look at this guy, in here we have a certain amount of pressure. And if I push this, the pressure in here has now decreased, and we know that this feels colder, right? If we look back at Gay-Lussac's law, pressure and temperature are directly proportional. So if I decrease the pressure in here, that decreases the temperature in here, and this actually feels colder. So that gives us an idea that energy and pressure are connected. And now with this new formula, we know that work and pressure are connected. So if we take a look, if we squeeze, if we increase the pressure, then that's going to add energy into these particles. If we decrease the pressure, that's going to release energy from these particles, because pressure, volume, and temperature, and temperature is a measure of kinetic energy, are all related. So if we take a look at here, we know that pressure is in either kilopascals, atmospheres, or millimeters of mercury. We know the volume is some type of length cubed. So if we look at work, pressure times change in volume, we get, in this case, they're doing newtons, which is force, per meter squared, which is area. And basically, we can connect these with joules, which is our primary measurement of heat. So if we take pressure times change in volume, we would get atmosphere per pressure times liters. And we can convert this to joules by using this conversion factor right here. If we have liter atmospheres, we multiply it by 101.3, and that gives us joules. So that's a key thing. Does anybody remember 101.3? What does that mean to you? Does anybody remember that conversion factor? It's actually the Pascal. If you remember, if we take a look, 1 atmosphere is equal to 760 millimeters of mercury, is equal to 101.3 kilopascals. So that's a way that after we find this work, we can change and convert that into joules. Potential energy, energy due to position. For us, that potential energy, where is it? That potential energy is a little bit different. Give me 1 second. So we take a look. Actually, I'll just do it right here. Right? If I lift this up higher and higher and then release it, that potential energy changes into kinetic energy. That's energy due to position. Kinetic energy is energy of motion. It's 1/2 times the mass times the velocity squared. Right? If we take a look, this right here is it's a 45 caliber cartridge. Inside of here, there would normally be gunpowder. That gunpowder also has potential energy. Now, the potential energy for the gunpowder, we call it chemical potential energy. It's not due to position of the object, it's due to position of the bonds. When those bonds break and reform, energy is released. And basically that gunpowder will produce a gas. It produces heat, which causes the reaction to continue. And as that gas expands, it pushes out what we call the bullet. So this is the casing, and this is the bullet. That pushes that out. Now, again, it changes that potential energy into kinetic energy. Now, obviously, you know, the fastest I could probably throw this is maybe 29 miles per hour. You know, I'm not a pitch or anything. So the fastest I could throw this is about 29, 30, 35 miles per hour probably. But we look at this and it doesn't seem like that much. If I threw this at you, it wouldn't do much damage. The mass of it's pretty small. The velocity of me throwing it also quite small. The difference is that whenever this potential energy is changing this into kinetic energy, the velocity of this is quite fast. We're talking 500 to 700 miles per hour. Well, keep in mind that it's the velocity of this squared that changes that kinetic energy. So that gives us a huge amount of kinetic energy. Even though the mass is small, the actual velocity of it would be quite large. I think whenever we discussed the kinetic energy in X a year ago or 2 years ago, if you were in there 2 years ago, we talked about which one has more kinetic energy, a poodle traveling the speed of light or a dump truck traveling 1 mile per hour. Well, in reality, I mean, it's a poodle traveling the speed of light. If a poodle traveling the speed of light were to hit a dump truck, yeah, both would be basically destroyed, right? That poodle's going to lose a heck of a lot of energy pretty quickly, but yeah, the dump truck is going to be severely damaged as well. Again, potential energy versus kinetic energy. There's so many ways to store energy and to look at kinetic energy. Let's take a look at this guy right here. This is a, let me switch this. This is a hand crank generator. So I'm using stored energy in my body in the ways of food or calories or whatever. And I'm changing that to mechanical energy. If we take a look here, with this, I've got another thing with it. And this thing has a string on it. And let's see if I can do this. Oh, almost. Let's see if I can keep it straighter. You can see that my mechanical energy is winding up this string. And my mechanical energy is changing into electrical energy and then into mechanical energy. And I'm able to lift this up and give this thing potential energy. Now, as that goes down, we can see that that has potential energy because it is stored energy. And that potential energy can then change into mechanical energy or kinetic energy in our case. Let's see if we can do this. I wonder. Yeah, it was able to actually turn this crank whenever that fell. We could use that also to power electricity and different things as well. The first law of thermodynamics basically says that energy cannot be created or destroyed, only change forms. So if you take a look here, it may be a review of like 6th, 7th grade science, but we have heat energy, a form of energy associated with changing the temperature. Thermal energy, same as heat, and it's also used when discussing the motions of molecules in solids, liquids, and gases. We're going to discuss all of those aspects. Radiant energy. Radiant energy is basically electromagnetic radiation. This is heat energy that can pass through space. Now, a better way to say that is to pass through a vacuum. What, 2 C's or 2 U's? I'll just put something that looks like a C and a U in there. So if we take a look here, that's a little bit different. A lot of times we look at heat energy. If I rub my hands together, that creates heat through friction, right? The difference with radiant energy is you have electromagnetic radiation, EMR. This can actually pass through the vacuum of space. That's pretty huge. There are 2 types of ways, excuse me, to transfer heat. One is called conduction, and that is through touch. The other is called induction. And basically with this, we can actually have it through space. It doesn't have to touch it. This would underlines what we call convection, and it does get a little bit weird. Convection is movement of currents. So you've heard of convection oven. Now in reality, is the hot air or hot fluid that's moving around, because convection deals with fluids as well, like with gases and liquids. Is it touching it? Yes. And then you have a radiant, which would be like the microwave. Now, how does the microwave work? Well, microwaves put out electromagnetic radiation in the microwave field, and those frequencies cause water molecules.
If you're writing stuff down, can you show us?
Yeah, I can show you the terrible stuff I'm writing down, but yeah. Yeah, it's not much great, but the electromagnetic radiation in the microwave spectrum is going to excite water molecules and cause them to vibrate. As they vibrate, just like me rubbing my hands together, those water molecules are going to rub against each other and produce heat. This is why they always say, like, you know, if you're trying to microwave something and you can add a little bit of water, it's better. This is also why, well, I mean, microwaving French fries is just terrible anyway, because there's not a lot of water content in it. It's a lot of oil. So you're better off like putting those in the oven or something. But yeah. Electrical energy. As you saw before, you know, you can take mechanical energy and change it into electrical energy, or you can also take electrical energy and change it into mechanical energy. It goes both ways. You've heard of electrical generators. So there are 2 major types of, well, let's go 3 major types of electrical generators. One is the one that you could buy, which is a gas-powered thing, which runs off the combustion engine and basically turns a crank and creates electricity as that turns. The other one is a hydro, like a hydro dam. Basically, water turns that crank instead of the combustion engine. And then the other one would be a wind turbine. But basically, you have them turning something in a magnetic field, and that causes magnetic induction, and basically causes electrons to move, and that's your current. That's your electrical current. Vibrational energy, we usually talk about this when we talk about if you have something in a solid, which are very tightly packed. They have some form of energy because they're not at absolute zero. These particles will be vibrating in the least. If they are liquid, they can move by one another, and they will have more vibrational energy. And if they're gas, they're flying away from each other. Thermochemistry is the study of thermal energy. That's basically what our unit is. The cool thing about this is when we talk about chemical energy, energy is stored in these bonds. When these bonds break and reform, energy can be released. And that's the biggest thing about what we discuss. We also know that at 0 Kelvin, there is no energy, and a lot of things around us are not at 0 Kelvin. So if we take something that's very hot and we put it next to something that's cooler, energy will go from the hot object to the cool object. All right. So we have something we call entropy. There's basically three big things. There's, well, two major things that we're going to discuss, but enthalpy and entropy are two major things that are discussed in thermodynamics. We're going to start with enthalpy. Enthalpy is basically heat content. Delta H is the change in enthalpy. We will refer to it a lot of times as Q. To find the delta H, you usually take products minus reactants, and there's something you'll see here. It's basically an alphabet thing. Products minus reactants. There's only one exception to this, but it doesn't apply directly. Basically, if we take the bonds and we break them and we reform them, the energy of the products minus the energy of the reactants will be the change. If the products have more energy than the reactants, then delta H will be positive, which means that we added energy to the system. If the products have less energy than the reactants, then delta H will be negative, which means we lost energy during the reaction. So that's a huge thing. And again, I've said this several times, but it's a state function. The value is determined only by the state of the system. We're not worried about anything else. There's basically what this is saying is it's the state of the system as it is. It doesn't matter how you got there. It doesn't matter how many paths you took. It's a value determined by the state of the system. So we can determine this enthalpy in many, 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 many different ways, in other words. So we talked about the system. I drew the box earlier. That's what you're studying. Keep in mind that if the system feels warm, it's losing energy. That's exothermic. If the system feels cool, it's taking energy. That's endothermic. It's all about the system that you're studying. The universe is basically not the system. Well, okay, I can see this. Surroundings. Basically everything, if you add up everything, let's do this. Universe is the total of all those things. So system plus surroundings. Surroundings is everything else in the universe except the system. So for this, we know that there are 5 normal types of reactions. for this unit, there are two. There's endothermic and exothermic. If heat flows into the system, it's endothermic. Delta H is positive. If heat flows out of the system, it's exothermic. Delta H is negative. So if we take a look at these examples, we look, delta H, negative 291 kilojoules. This would be exothermic, easy enough. If heat is added as a reactant, that means that heat's being brought into a system. The products have more energy than the reactant. That means we are dealing with endothermic. If you look at the system versus the surroundings, your body, when you step outside on a cold day, your body is going to lose energy. Your body is stressified. Cup of soup in the microwave, we are adding energy to that cup of soup. That is endo. This reaction has heat as a product. That means that heat is being released. So that is exo. And if we take a look here, delta H is positive. That means that we have added energy into the system, and that is endo. So those are basic quick questions. Delta E, basically change in energy. It must equal the sum of Q, which is heat, plus the work. Again, if we have another way to figure that out, we take the products change in heat minus the reactants, and that gives us the change in enthalpy. So if we look at this, one of the biggest things is the positive and negative signs. So it's always from the standpoint of the system. Energy flowing out, sign is negative. Energy flowing in, sign is positive. Work done to the system, the sign is positive. So if we, for example, take this and put work in there, remember, I just increased the pressure of that by decreasing the volume. I added energy into that. We talked about before, if we decrease the pressure, we know that this can gets colder. If we were to somehow increase the pressure in this, then it would get warmer. If you've ever pumped up a bike tire or something like that, and you felt like the tubing afterward, it feels warm. Or if you feel a balloon or something like that and you go, it feels warm afterwards. Now you might say, well, it's warm because, you know, the air that I'm putting in there is upwards of 15 degrees above room temperature, Celsius wise. But it's also that increase in pressure. So keep in mind, if the system does work, then the sign for work is negative. And that will kind of fix itself out with that, that negative sign in front of the pressure and change in volume for work. In chemistry, Q and W always reflect the system. That's our key thing. We want to make sure that we understand that system thing, especially when it comes to the signs. It says, in this diagram, work is being done on the piston from the surroundings. So we take a look at the piston, and we have compressed the system. That means that we are giving the system energy. The sign of W would be positive. We take a look here. The system is doing work on the surroundings. So as this expands, it releases energy. So let's take a look here. Calculate the amount of work done when a balloon with a starting volume is 10 milliliters. If it's expanded to 1.55 liters, if the external pressure is 0.976, calculate the amount of work that is done in joules. So let's take a look. We went from 10 milliliters in the balloon, and we're looking at the balloon as the system, to 1.55 liters. So did the system do work to the surroundings, or did the surroundings do work to the system? Well, look at our examples up here. Did the volume get smaller, or did the volume get bigger?
Bigger?
Yeah. So the system actually did work to the surroundings. So if we take a look, we can actually determine the sign of the work. The sign is going to be negative because the balloon did work to the surroundings. We'll be able to see that when we calculate it as well. If we take a look, the pressure is 0.976 atmospheres. And we're going to multiply this by the change in volume. Now, again, we have liters and milliliters. So we want to change this to liters. 1, 2, 3. Now remember here, we have final volume minus initial. So 1.55 minus 0.01.
The answer is 1.54.
1.54 times 0.976.
It's about 1.503.
Let's see here. 3 significant digits. This would have 2 decimal places, but 3. So yep, we get 1.50. That is negative, and that is liter atmosphere. Since we probably want to change this to joules, remember, every 1 liter atmosphere is 101.3 joules. 1.50 times 101.3.
It's 151.95.
So it would be negative 152 joules. Questions there? A cylinder at a pressure of 1.32 atmospheres has a volume of 4.19 liters. When the external pressure on the piston is increased to 3.52 atmospheres, calculate the new volume and the work done. So we have pressure and volume. So we have P1 V1 equals P2 V2. These are our P1 and our V1 and our P2. So if we're solving for V2, We divide both sides by P2. 1.32 times 4.19 divided by 3.52.
It's about 1.5712.
1.57 liters is our second volume. So that means that we went from higher volume to lower volume, so work was done on the system. So if we take a look, work equals negative P times delta V. If we take this 1.57 liters, which is our final volume, and minus the 4.19 liters, which is our initial volume, times it by the pressure at the end, (1.57 minus 4.19).
The answer is negative 2.62.
Negative 2.62 times 3.57.
The answer is negative 9.3534.
The fact that that negative sign is there, that means that we will end up with a positive overall, which makes sense because work was done to the system. So we get 9.35. That is atmosphere liters. 9.35 times 101.3.
The answer is 947.155.
It gives us 947 joules of work. When fuel is burned in a cylinder that is attached to a piston, the volume expands from 0.286 liters to 1.69 liters against an external pressure of 2.34. So it expands, so that means that work is done by the system. (1.69 minus 0.286).
It's 1.404.
1.404 times 2.34.
It's about 3.2853.
So right there, that is the amount of liters, atmospheres of work done. In addition, 125 joules of heat energy are released. So is that positive or negative?
Negative.
You got it. It says released, so that's going to be negative. And our work, is that positive or negative, or is work being done by the system or to the system?
It's negative and by the system.
It's by the system. So whenever we do this, we're going to find that delta H equals Q plus W, which is the amount of heat plus the amount of work. The problem is this is in joules. So we have this in liters per atmosphere. So what do we need to do? We need to multiply it by 3.29 times 101.3.
The answer is 333.277.
This has 3 decimal places, so this would be significant to the ones place. Negative 1255 plus negative 333.2.
It's negative 1,588.2.
That is to the, let's go ahead and rewrite that. That is to the ones place. So we take a look. The energy for burning that fuel, it released 1,588 joules, or 1.588 kilojoules. Questions there? I think that's going to do it for today. By all means, I suggest that you read through this and take a look at the signs, because that is going to come into definite play. Didn't get as far as I planned today, but I always plan more than not. Tomorrow will be a nice review day of calorimetry and what we call specific heat capacity. And basically that is, why hot potato soup will burn your mouth a lot. And you have to make that stupid face where you're like sitting there doing the weird thing with your tongue versus French fries with the specific heat capacity of the oil that has basically replaced the water in the potato. Get cold very fast. If you have any questions, by all means, stick around. Otherwise, get out of here. Questions, William? Questions, Cassidy?
Oh, thank you very much.
Hey, thank you, man.
Have a good day.
You too. I'm going to go ahead and end this so that I can save that recording. I'll see you guys. Bye.